Solutions for perfect problem 5 for Math 251. A couple questions here. The first one is to kind of prove or derive, or I guess I say the word show, verb, that the derivative of arctangent of x is equal to 1 over secant squared of arctangent of x, which it turns out is equal to 1 over 1 plus x squared. Okay, so let's do that. What we can do, so this is part 1 over here maybe, is we'll start by letting y be equal to the arctangent of x, and our goal will be to find y prime. It's essentially using implicit differentiation, as I note here in the hint. And so there's a problem. You can't just take the derivative of both sides of the equation, because you'd have to take the derivative of arctangent of x, and you don't know the arctangent of x. You're trying to show that it is this. You can't assume that it's that to show that it's that. So what I got to do is kind of mess with both sides of the equation until I get things that I can take derivatives of. So what I'm going to do is take the tangent of both sides of the equation to get the tangent of y equals x, and now I'm going to take the derivative of both sides of the equation. So the derivative of tangent we know to be secant squared. So the derivative, that's the derivative tangent of x is secant squared x. So the derivative tangent of y is secant squared y times y prime. That's really an application of the chain rule. My outside function is the tangent of x, and my inside function is the letter y, I guess you could think of here. Anyways, y prime you could solve for by dividing both sides by secant squared y. So I get that y prime is 1 over secant squared y, which is kind of weird defining y prime in terms of y, especially since I just made up y. It's what I'm calling arctangent of x. So I could substitute in and say that y prime is 1 divided by secant squared of, and then instead of writing the letter y, I can say that y is arctangent of x. And I think that was my first equal sign. Yeah, there we go. So partially done. The claim is that that's equal to 1 over 1 plus x squared. It is. It's not really a calculus problem to show that that's true. It's a Math 112. It's a trig problem. But what I want to do is I want to simplify secant squared of arctangent of x. And the trick to doing this is we're going to do substitution. So pick some letter t maybe, and let that be equal to the arctangent of x. Maybe I should have used y since I used that above. Whatever. So to simplify this, well, if t is this stuff inside the parentheses, this stuff just simplifies to secant squared t. Wait, that feels like I just kind of cheated. Well, sort of, because t is something you made up, but you can use the fact that t is arctangent of x to figure out that the tangent of t, if you take the tangent of both sides of this equation, you get that the tangent of t is equal to x. And when I have trig functions, tangent of t equals something, I prefer to write it as a fraction because I know that I am going to draw a triangle. Not just any triangle, a right triangle, where I label one of the angles t, and then use this fact to label some side lengths. If the tangent of t equals x, the ratio of the opposite side to the adjacent side, that's the TOA in SOHCAHTOA, is equal to x over 1. So I have to choose lengths here and here so that when I divide the two of those guys, I get x over 1. Easiest way to do that would be call this one x, call this one 1. Then I can figure out this length over here. Do I need to show that separately? No, I don't think I do. Yeah, I will. It'll turn out that if this is 1 and this is x, this is the square root of 1 plus x squared. Maybe I'll call that h or something. Where that comes from, how about c? Those are easier to write than h's. That comes from the Pythagorean Theorem. It says that if you know two sides of a right triangle, you automatically can figure out the third side, because a squared plus b squared has got to be equal to c squared. So if I take the square root of both sides of the equation, I get that c is equal to the square root of 1 plus x squared, which is what I threw up here. Okay, so here's a picture of a triangle with an angle t in there. I can use that to figure secant squared of t. And the way I'll do that is secant squared is 1 over cosine. So this is really 1 over cosine of t squared. And using SOHCAHTOA, I know that the cosine of t is the length of the adjacent side, 1 in this case, divided by the length of the hypotenuse, which is the square root of 1 plus x squared. So I got this. And I can simplify this fraction a little bit. When you're dividing fractions, you multiply by the reciprocal. This whole mess of fractions inside fractions here simplifies to the square root of 1 plus x squared, and that's being squared, so that's just equal to 1 plus x squared. And note that this whole thing was to simplify secant squared of arctangent of x. I just showed that the secant squared of arctangent of x is 1 plus x squared. So up here, when I said that y prime is 1 over secant squared of arctangent of x, I could have equivalently said it's 1 over, and then instead of writing this, write what this is equal to, 1 plus x squared. What I just did is proved this derivative. Done with part 1. Okay, and then for part 2, there was a typo in here. I just went and fixed it. There should have been a 1 over a in front of each of these arctangents right here. I don't have to redo the whole video, although I do have to admit I screwed up, I guess. Everything that I did before still works, but now for part 2, really what I'm being asked is to take the derivative of, not arctangent of x over a plus c, but rather 1 over a times the arctangent of x over a plus c. Okay, so to take this derivative, I guess the first thing you notice is that you have the sum of two things. Well, I'm going to do 2 steps at once. I have a constant right here out in front, so I'm being asked to take the derivative of a sum. Well, that's just the sum of the derivatives. It's the derivative of this thing plus the derivative of this thing. True. And the derivative of this thing is a constant times something else, so I can pull that 1 over a out in front. I can say that this is 1 over a times the derivative of arctangent of x divided by a. Maybe a little overkill, but fine, plus the derivative of c. Isn't the derivative of c just 0? Yeah, it is. I'll get there, don't worry. Okay, so in this step, you're taking derivatives. We'll leave the 1 over a alone because that's not inside these parentheses. And really, we're trying to figure out the derivative of the arctangent of x over a. And what we'll use to figure that out is the result from part 1 and the chain rule. If it were just asking me the derivative of arctangent of x, I could say it's 1 over 1 plus x squared. But it's not. It's asking me the derivative of arctangent of x over a. So playing the role of this x right here is this x over a. I got 1 divided by 1 plus, and instead of x squared, I got x over a squared. But then I'm not done. I still have to multiply that by the derivative of x over a, the inside layer of my chain rule right here. And then you still got this derivative of the constant out here. Okay, in this step, I guess I still have 2 derivatives to take, the derivative of x over a and the derivative of this constant. This one, you're like, take the damn derivative already. That thing's not that hard. It's a constant, its derivative is 0. You're right. Okay, I'll do it. Settle down. But this one, the derivative of x over a, might give you a little bit more trouble, unless you can think to view this as 1 over a times x. So this is the derivative of a constant, 1 over a in this case, times x. I'm going to write that. 1 over a times 1 over 1 plus x over a squared times the derivative of 1 over a times x plus the derivative of a constant, which is just 0. And the reason I wrote it like this is I think now it's more obvious that you can pull the 1 out over a in front of this derivative, take the derivative of x, which is just 1, and get 1 over a times 1 over 1 plus x over a squared times 1 over a. In other words, you got 1 over a squared, that's this 1 over a and this 1 over a, times this mess. Well, this mess right here I can simplify a little bit. Instead of thinking about this as a 1, I can think about it as a squared over a squared. Why in the hell would you think to do that? Well, because this one, x divided by a squared, is the same as x squared over a squared. And now I got a common denominator down here in the denominator of this big fraction. So I can rewrite it as 1 over a squared times 1 over a squared plus x squared divided by a squared. And maybe this top 1 right here, I'll write it as 1 over 1. So it looks more like a fraction over a fraction, because the way you divide fractions is kind of like multiplying, which multiply by the reciprocal of the denominator. What I'm saying is this mess of a fraction right here is just a squared over a squared plus x squared, which I can cancel out these a squareds, and what I'm left with is exactly 1 over x squared plus a squared, which is what I was trying to show. So there you go. The derivative of this mess is this mess. And what you need to be able to do that is the derivative of arctangent of x, which we could find using implicit differentiation. So I guess that ends this problem here.